just in front like this. Okay. Okay. So first of all, I'd like to thank. Primarily, I would like to thank organizers that they gave me the opportunity to present the work. Just correct me if I'm talking about something unrelated, because I got up at 4 a.m. On the way, I lost my luggage, and I don't feel like this is a good day, but okay. So I will talk about something that hopefully nobody yet discussed that much in here, meaning I will present a couple papers related to pseudogauge transformations. One of the problems that we recently seem to study and be concerned when talking about constructions of relativistic hydrodynamics. Okay, so this is a kind of, I have to make this tradition and show the most boring plot probably ever, but this is really the, maybe looks boring, but this is the point of our, all of us being probably here. We want to study what are the properties of matter in equilibrium, primarily. And this is, as we all see, not easy to do. We have a two-dimensional diagram which we need to study. And first of all, okay, I maybe went too fast. First of all, we are used to talking about presenting our motivations for what we are doing in terms of the early universe and etc., etc. This is very kind of interesting and motivating, and also for publicity very nice. We want to tell that what we are studying really can tell us something about the beginning of universe, and this is what happened in this lower left, the left side of this diagram. Meaning the universe cooled down, and it brought us to the universe as we see all now. On the other hand, if we go along the other axis, we have some systems which are actually reproducible, but they are just sitting there, meaning there are neutron stars and other compact objects which we can study very indirectly. And apart from these two, we have our numerical tool, kind of a numerical experiment that we can do on the computer, and we can try to simulate QCD on the lattice, and then we can learn something within this region. But there are some problems to go really deep into this region where the matter is filled with net baryon density. Now, probably the most useful way is just to use heavy ion collisions, which are by changing the system size, the system's energy, we can try to really probe quite broad region of this diagram, but the problem is of a different kind. These systems are quite, most of the time, not in equilibrium. They are quite dynamical. They traverse through this diagram in a non-trivial way. And why? Of course, this is schematic. I mean, yeah.
Yeah, perhaps to be more realistic, one should draw. Perhaps we may enter the block with some low energy, but we don't know.
No, I agree. Of course, I mean we are. Okay, these slides were borrowed from some slides given to some mostly people unrelated to what we are doing. So I felt like I'm not doing a big mistake. But since we are no, I agree. I agree. Uh, what I just wanted to say is it's not really like we are colliding systems and this is a dot on this diagram. This is completely like a probably some cloud moving towards this diagram, and out of this we need to infer what was the property at each point, and this is extra hard task in my opinion too. So probably we are still ahead of many discoveries. So what I wanted to maybe, I don't know why it's okay. What I wanted to stress is that this is what we observe in the experiment. I mean, we make these collisions, we observe thousands of particles in a form of their four momenta. And out of this, we need to infer what was actually the initial state. And we don't know much on the way what happened. And what I want to stress also, I don't know why it's not working properly, is that out of these pictures, we can really see that we really give the meaning to the densities of the currents in heavy ion collisions. It's not like this that we kind of, it doesn't matter what is the distribution in the initial state, and out of this we can get the observables. We need to know this initial state, and we need to actually know it very well to get the properties as we get the observables as they are measured in the experiment. So this is kind of important point that I want to stress, is that we assume that those currents really have some sense at the femtoscale. Okay. I think these slides are too large, that's the point. Okay, so out of this many points, experimental points, we are able to pin down what are the properties of the produced matter. Of course, within some error bars, we get more or less that the quark gluon plasma viscosity is close to the lower bound, known from elsewhere, by the way, also. But there are many properties that are still not known. In particular, what are the dissipative properties of the produced systems, and this is still an ongoing study. And among all these kind of tasks that are still ahead of us, it is very useful to have some extra constraints. And these constraints are not easy to find. It's not easy to find observables which will be sensitive to some things and not sensitive to others, so that we can give a new let's say switch that we can switch on and switch off and check what will be the impact of this. And recently, actually, it was found that that one of such new switches that allow to study the matter much better, probably will allow to study the matter much better, is the orbital angular momentum, which is initially pumped into the system when we collide it in the when we collide non-centrally heavy ions, and if this angular momentum is being transferred to the plasma, then we expect that it will also have some impact on the final observables through the particles which are being measured. So we assume that if there, I mean, this initial orbital angular momentum is there, the question is if it's transferred to the plasma, how fast and in what rate, and if it really does, then it should be visible in the final distribution of particles. And this was proposed, and then it was actually measured. But apart from this, there is another important property that is also allowing us to study this system, is that apart from initial orbital angular momentum, there is also initial magnetic field that can also come to the game due to the fact that those initial ions, collided ions, are charged. Now, this is really irritating. There is also another point which is important, is that if you have initial particles being produced, then they are oriented according to their magnetic moments and not spins. And this means that if there is this initial magnetic field created, then actually the initial orbital angular momentum will orient the spins, but this effect will actually split the spins, spin polarization, which means that if there is initial magnetic field, this could be also giving another effect in the observables. Now, this was this proposed effect was measured first by STAR, and then this measurement was actually a negative measurement. So after repeating this measurement with better precision, it was found that actually it is really what is happening in the reality. So this is the polarization along this direction of the initial orbital angular momentum, and basically we observed that as a function of the energy in the collision, we see that this polarization actually decreases as a function of energy, and this was actually I would say a breakthrough measurement, because it was first this kind of a measurement of the polarization in the system of at the femtoscale, and not really the polarization, the measurement of the magnetic moments orientation in the heavy ion collision. So this really is a measurement that provides another way to study the properties of quark-gluon plasma. But now comes the question how this transition from the orbital to the spin part takes place. And now it was proposed that if the system is initially in equilibrium, but not only in the momenta, but also in the spins, then this polarization can be given by the initial vorticity in the system. And starting from the Pauli-Lubański definition of the spin vector for a single massive particle, we can see this kind of familiar expression. The spin vector is given through the total angular momentum operator and the for moment. Now, oh, Jesus Christ. Okay, so it was found that actually the mean spin vector for the emitted particles is given through the following expression. So you have the integral over the hypersurface with the basically equilibrium distribution functions for fermions. And the key quantity which gives rise to this polarization is the gradient, the anti-symmetric gradient of the velocity of the fluid elements, which is this omega, this var pi, right? This quantity is called thermal vorticity, and this is anti-symmetric combination of the gradients as it's given here. And basically, this formula allows us to calculate what is the polarization in the final state in terms of the gradients of the flow at the final moment before the hadrons are emitted from the plasma. Assuming that there is not much impact from the decays, which may happen, of course, in here, then you can basically plug in the gradients of the for velocity of the fluid, and then you can calculate what is polarization vector of the emitted particles. And using this, okay. And using this, one can actually determine what is the spin polarization of the final particles. And this different colored lines, which are being plotted on this same result, experimental results, which are the points in here, basically show us that this picture works very well, meaning that it signals that probably the idea that the spins are in equilibrium at the same rate, I mean, they are equilibrated at the same rate as momenta of particles, they are is really what is happening in heavy ion collisions. But this concerns the global polarization, meaning that this quantity basically describes what is the polarization along the initial orbital angular momentum direction. But the question is, of course, whether this is a general property which one can use to study polarization, for instance, differentially as a function of different quantities. Now, what I mean is that in general, you can have different local flow structures in the system. Apart from this initial vorticity from the orbital part, you can also have the initial vortices, small distribution of small vortices in the transverse plane, and this basically results from the geometrical like structure in the transverse plane, this almond-like shape, and then you would expect that this vorticity pattern would also be visible in the experimental data. If you look along the z direction, there can be actually, we know very well that this probably is not really true. This is what is more real. You have some granular structure, and then these vorticities should be integrated over many collisions. But there are also possibilities like this where you have the traversing highly energetic parton, which also generates this kind of structures. So in general, you can have very different mechanisms which give rise to the vortices in the system. And then the question is whether you should expect that the same relation that this should trigger the polarization in the final state will be also seen in here. Okay, basically, so this on the left-hand side, this is the measurement of one of these properties which I discussed. So if you have a transverse plane and you have vortices, on average, of course, vortices in the transverse plane, they should give rise to this kind of pattern with the positive, negative polarization along the direction of the beam. And this was what this on the left hand side, you can see what was measured in the experiment by star, and you can see indeed that this pattern is there. But the problem is that this kind of naive picture with this, which could lead in principle to this variation of the polarization is not really true in general, because in relativistic systems there are different components of the force velocity, and in principle you can find that for relativistic relations this pattern is not what is really being what one can get from the theoretical modeling. On the right hand side you can see results of, in the top, the hydrodynamic modeling, and in the bottom you can see some transport results, and both actually, due to the fact of relativistic effects, they give some different signs. Now, no, it's not the matter of me being far away. Okay, but so this, of course, this result was kind of a problem, but then it was actually proposed that in this initial local equilibrium formula for the polarization of the outcoming particles, there was a missing part, which was the part related to the symmetric combination of the gradients of the force velocity, and then you should actually include it to get the proper result. This part in red is already this known part, which was related to the thermal vorticity, and the other part is the one which is related to some part which is a symmetric combination of the gradients. Now the problem is that this part, this extra part related to the symmetric, the shear, thermal shear part, has different structures of different form depending on how you try to derive it from first principles, and this basically give rise to the, I would say, motivated the field to find some solutions, a different kind of solutions to the problem of not capturing the experimentally observed effects properly. So the proposal was to assume that actually the spin which is being generated in the system, the spin polarization which is being generated in the system, actually follows its own dynamics during the evolution, and it's not being bound to the gradients of the force velocity. This gave rise to some proposal that of so-called spin hydrodynamics, and this was first done in this paper in 2018. The idea was that you can take distribution functions and you can generalize it to the density, spin density matrices, and then the formulas which you can find in equilibrium, where usually one would expect the thermal vorticity to be present. Now you can exchange it. You can actually find that this should be an extra Lagrange multiplier, which some people termed the spin polarization vector, the tensor. Now, the point is that this extra quantity now behaves as a usual hydrodynamic quantity, such as temperature or for velocity, and it can, in principle, follow its own dynamical equations. Okay, since then, hydrodynamics was developed by many groups, and it's really dynamic, I would say, development. But what is basically the idea? The idea is to generalize the usual methodology. The hydrodynamics is basically the theory, the effective theory for the conservation laws you have the conservation of charge, conservation of energy and linear momentum in the usual hydrodynamics, which should be satisfied, and to do so, you have to introduce the Lagrange multipliers, which basically are fixed on during the evolution in such a way to satisfy those equations. Now you can generalize it, and you can try to include now additional evolution equations which will follow from the conservation of total angular momentum. You have now an extra rank 3 current, which should be kind of a total angular momentum of the system, which in principle, to be satisfied on the evolution, should also be connected with introducing additional Lagrange multipliers. And this could be a kind of analogs of spin chemical potential, but in this particular case for the angular momentum orbital and spin part. Now, these equations, of course, can be written as a kind of effective-like theory. So if you know how to construct these currents, and then you just postulate that those currents should be conserved, you can do so. You can write those equations, and then you can, in principle, construct and solve your hydrodynamics in this way. But if you go deeper into this, then you should realize that the same structure and Lorentz transformation properties of this current should also have some analogs in the at the level of the field theory, and then basically you expect that there should be some relation between the field theory definitions of the currents and your mean values of the currents, which in principle, if you know how to construct the state of the system, then you may obtain them by just tracing the operators with the operator for the system. Now, the point is that if you get these currents, you would expect that the same properties, the Lorentz properties, out on both sides, on the field theory side and on the side of the effective theory, should be somehow preserved. So how to do that? In principle, you can start with the usual methodology, starting from the Netter's theorem. You start with the action, and then the Netter's theorem tell you that the invariance of this action, basically with respect to the group of global transformations, will result in the conserved currents. And these currents, in principle, if they are found, if the mean analogs of these currents are found, then this give you the conservation laws of the form which we are usually dealing in the hydrodynamic picture. And the corresponding conserved charge related to this current will be the generator of the transformations. Now, these currents may be constructed in different ways. The point is that from the Dirac-Lagrangian of non-interacting fields with spin 1/2, let's say that this is the first approximation, and we start with the simplest possible system. You can write down your Lagrangian density. You can use the Netter's theorem, and then you will get your currents in the following form. They are called by the procedure, they are called the canonical currents, and they are conserved. The problem at this level is that obtain the energy momentum current which you will get from this procedure is not symmetric. This is the first problem which may be overcome by some other procedures I will talk about later, but also the spin tensor which comes out is not conserved. Now, if this tensor is not conserved, that you may actually prove that the global spin will not be Lorentz covariant, and as a result, you cannot define the spin density in the system in such a way that it will not be dependent on the hypersurface at which you calculated. Now, those, however, those currents, the energy momentum tensor and the spin plus the orbital part are conserved. So you can basically use this as your equations of motion for starting from when starting to construct the hydrodynamic theory. But the problem remains how to divide, how to shift the orbital and spin part between these two contributions. Another problem related to that is that you can also perform a transformation to those currents using the so-called pseudogauge transformation. You can use so-called superpotentials, or in general, there are just currents which are constructed out of the fields in the theory. You may always add total divergence in the energy momentum tensor, and you can also add a similar term in the spin tensor. However, performing this transformation will also always will always fulfill the conservation equations, so this will not be affected because of this structure. And also they will, by integrating over hypersurface, they will give you the Poincaré algebra generators, and they will give the generators always in the same form. So basically these two properties are always fulfilled, but however this freedom for shifting the spin and orbital part of the angular momentum remains. And okay, so of course this topic is not new. It was addressed by many groups so far, but both not only in heavy ion physics, but both in heavy ion physics and also in the topic of the nucleon spin, where similar problems arise. But I would say that so far there is no consensus how to solve this problem. There are different gauges that are commonly used. However, in my opinion, none of these gauges is, I would say, preferred, or there is no consensus which one should be preferred to use in practice. For instance, in Einstein's general relativity, one would expect that the energy momentum tensor is symmetric, and this is obtained by the so-called Belinfant-Rosenfeld symmetrization procedure. You can do this by using this kind of form of the superpotentials, where one of the potentials is basically the spin current, and in this way you get rid of it completely, and the other one is zero. In this way you get the symmetric T mu nu, and you have the spin current which is basically not present at all in the theory. So you shift all the angular momentum into this orbital sector. So this is unfortunately not something that is satisfactory for if you want to construct the hydrodynamics with some non-trivial spin evolution. Another pseudogauge which was also commonly used was resulting from the problem that basically if you have the canonical currents, the spin current is not conserved. So it was proposed that one can introduce this kind of potentials in such a way that you have the energy momentum tensor conserved now, but and the spin current is sorry, the spin current is now conserved, but energy momentum tensor is symmetric. This was called the Groth, Van Leeuwen, Van Wert pseudogauge, and it actually be also found from the quantum kinetic theory approach, as well as from the classical kinetic theory, if you consider the phase space kind of extended to the spin of the particles. Now, another pseudogauge which was also considered was Hildebrand-Wojthausen pseudogauge. This one was giving similar currents as for the GLW case. The difference was that actually this resulted from the idea that you can construct them as kind of having in mind the fact that actually the Dirac spinors also satisfy the Klein-Gordon equation, and then the Dirac equations for the fields actually are used as a constraint equations to find these currents. And now these currents were obtained, but up to the first order in gradients, they allow to construct the hydrodynamic theory, which is more or less similar to what you would obtain if you start with the GLW forms. Now the global spin is the same both in the GLW and in the Hildebrand-Wojthausen case, and also the T mu is symmetric. Now the question is, of course, which one of these pseudogauges is anyhow useful, and even if it is useful, does it have any meaning, and whether it should be preferable to use any of them among the others. If you go to the book by Sidney Coleman, you will find that he says openly that there are many of these currents that can be constructed, and all of them should be equivalent. Now, maybe I will just use this. Okay, one of the ways to address this question is to ask the following question: whether the total angular momentum operators which you can construct for these parts of the angular momentum, for the total, for the orbital, for the spin, whether they satisfy the SO3 algebra for the equal time commutation relations. And this is something that you would expect if all of these quantities are observable. Now, but because they should in principle represent the quantities which are satisfying the same algebra that the usual angular momentum is satisfying. Now, you can do it actually for canonical spin, and trivially for Belinfante, it is known that these relations are satisfied, but it is not clear whether for GLW and HW those relations are satisfied. And you can basically what we did, we just tried to study this. You can define the total spin operator in this form. Basically, you define it as an integral over the volume in this case of the spin current, and then you can try to verify this relation. And what we found was that actually only for the canonical case this relation is satisfied. Both the GLW and HW currents are not providing these relations in the expected form. So the conclusion would be that if you want to study some spin dynamics at the quantum level, at the level of the field theory, you would rather prefer the canonical currents over the HW and GLW currents. However, I would say that if you want to construct some effective field theory, which will give you the hydrodynamic evolution, then in principle there is nothing against using the other pseudo gauges. In principle, the pseudo gauges which provide symmetric energy momentum tensor and conserved spin tensor could give you a good link to the thermodynamic and hydrodynamic approaches and be preferable over the canonical currents. Now, another question which one may ask in this context, in the context which of these currents is preferable, one can propose that maybe the experimental procedures will decide on whether any of them is better. But in fact, when we study heavy ion collisions, what we want to have are the phase space densities of the spin tensor, and this is actually can be obtained from the Wigner function approach. And if you write down the expressions for these currents, you can write the phase space density of the Pauli-Lubański for vector in this form, and then these densities are actually on the right hand side you have a total angular momentum density, and then you can see that actually if you put the both contributions from the orbital and spin part, actually the orbital part doesn't contribute to this equation, and you are left basically with the spin part. For the GLW pseudo gauge, you can calculate, it will give you this expression, and you can repeat the same calculation, and for the canonical spin tensor, it will give you the same result, and then concluding from this conclusion from this would be that maybe at the level of the Pauli-Lubański vector, which provides you the distribution of spin, will not actually matter which kind of pseudo gauge you plug into this expression. So from this study, it is kind of not clear, at least at the level of the studied pseudo gauges, which, I mean, we are left with this very small set of pseudo gauges, which is this GLW, HW, canonical, possibly also the phenomenological, and maybe some others which are not used really in the phenomenology. But if you take this small set, then you will find that they don't matter at this level. Now, yes.
I think we must make quite a clear distinction between the operator and the state. So when you measure the mean value of the spin polarization vector of some final particle, you're calculating an average. So the average is space or rho something depends on the operator and the state.
Yes.
The operator, as you have discussed here, because this is mostly related to the form of the operator so this is mostly related to what is the form of the operator, which tells you associated to the spin of a single particle as a function of momentum, and this is independent of pseudo gauge. I agree.
Yes.
But quantum state, on the other hand, is not. So the local equilibrium state, okay, of the plasma which hadronizes is different
I agree.
Pseudogauge, or say canonical, or infante, or
I agree.
Therefore, the mean value of the spin polarization vector does depend on the pseudogauge. And this was calculated by Matteo Museco in a paper 3 years ago.
Mm-hmm.
He calculated the mean value of the spin polarization vector for in 3 pseudogauges, and found different results.
Yes.
So there is a dependence on the final measurement of the pseudogauge.
I agree, but what I meant is in here is that you basically, if you have this momentum in here, then you can basically easily infer from this equation that always when you plug the part which will contain another momentum, it will always drop off at this level. I know that if you have the kind of, this is a final effect, so you just take your, as in the case of the Cooper-Frey formula, you can just take it, you can just calculate the distribution, but you don't ask yourself a question, what was before? This is what you mean. I mean, basically.
I could agree with that formula, okay? The total angular momentum.
Mm-hmm.
Sorry, the decomposition of the total angular momentum
into the orbital and spin part.
I agree with the formula if you remove the x. Okay?
Yeah.
So because if you measure the notion of density spin is unmeasurable when you have an experiment. So what the experiment measures is just the polarization as a function of momentum. They don't measure the polarization as a function of momentum. Okay,
but we touch a very delicate issue where we immediately will disagree.
No,
because
what I'm saying is that if you remove the x there, then you have decomposition of volume mass vector in momentum space, and I agree. And then you have the dj lambda nu alpha d3p, right?
Yeah.
Okay, this dj lambda nu alpha is the total angular momentum. The total angular momentum, of course, doesn't care whether you have
exactly.
Right?
Yeah.
Okay. I agree. What I'm saying is that is the operator part. So this is how you write your polarization of the function of momentum. Then you have the state. So what is the quantum state over which I average? And if you believe that this is local equilibrium, okay, local equilibrium unfortunately depends on the pseudogauge.
Yes.
So whether you have a Dagger infante or canonical, you have different expressions. And those expressions, they are not invited.
Sorry, maybe a comment. So we already discussed this.
Last week, yes.
And the issue was that local equilibrium, defined in that way, contains a lot of ambiguity, right? You are maximizing the entropy, keeping some stuff fixed. And I agree that depending on the pseudogauge, if you keep a T0 nu fixed, then it depends on which T0 nu you find, right? But that I think is not a problem of the pseudogauge language. That's a problem of an ambiguity when you introduce the concept of local equilibrium. If you have a language like, for example, the theory, which okay, maybe does not apply, maybe it applies only at late times and so on, then all the pseudogauges are equivalent because there is a one-to-one mapping from one kinetic theory to the other. And you can just solve the Boltzmann equation in one of those kinetic theories and be able to transform. The part that there is a high ambiguity in the states.
This is a debated issue, whether the kinetic theory leads to the formulation which is mostly used in practice is pseudogauge independent.
Well, there is a problem of calculation, right?
No, it's a problem, for instance, if you expand from local equilibrium. Okay. Whether this is
but we are simply back. So the concept of local equilibrium is I invent a density matrix once I know that I have a certain density, right? The fact that the procedure that I am using depends on the pseudogauge is a problem in the definition of local equilibrium. It's not a problem of the pseudogauges.
Okay, you have a better way of defining local equilibrium.
Well, you should have a language that, so this is some like connection coefficients or some corrections that make sure that whatever statement I make is manifesting true simultaneously in non-coordinate systems, right? I would like to make a derivative, but there are some coordinate systems in which the usual derivative becomes something else, and so you produce some connection coefficients. So I believe that we should rethink about the definition of local equilibrium, taking into account the fact that we need to introduce some counter terms when we make the Lagrange multiplier methods to make sure that what we get is manifest with pseudo-gauge invariant, just like we introduced the Christoffel symbol to make sure that the derivative is manifest with coordinate system invariant, right? But I wouldn't say that this is a problem of pseudo-gauge, this is a problem of how we set up a language to make an optimization when we define density metrics.
Okay, if you're able to find such an evolved theory of local equilibrium, that would be very grateful. I mean, of course, I would like to see some theory of local equilibrium where I'm completely independent of pseudo-gauge. But the only definition I know of local equilibrium is that you have some small system with some given mean value of energy, momentum, and charge. And the fact that when they have become, say, small, then the only thing I definition I can think of is that okay, we have some density of energy, density of momentum.
I get it, but the problem is that, for example, there is channel about it, right? That has its maximum entropy approach, right? But this might be maximizing the entropy density in the local aspect of the fluid using as information all the components of the fluid. You're doing something else. You're maximizing the entropy in the local reference frame that is orthogonal to the hypersurface where you're making the calculation, using as your only information.
You can try to set, you can try to constrain all the components, but then you won't have any. You won't have an empty.
No, but this is what I'm saying. There are some ambiguities in this idea of the local equilibrium, but that's why.
I don't.
We can postpone this, I think.
No, I'm also, this is the point what I'm talking about this. So now it will become even more weird because what we some time ago got interested into with Wojtek was that you can actually calculate the fluctuations in such quantum system. And okay, what do? You take you can have different pseudo gauges, and now you can have as many as you. I mean, not only those which I discussed. I picked up those because they appear in all papers which I read, but you can pick up any actually, and they are different. Actually, what they really mean is that you differently localize your currents. You just say, now my density goes in here and not in here. And it is all fine. You can pick it up as a kind of definition of yours. But now, since you have a quantum system, you will have fluctuations if you go to very small sizes. And now you can take various components of your current densities. You can pick up any of your favorite ones. But what we just, for simplicity did, we just pick up the time component of the energy momentum tensor, and which is related to the energy density. And we defined the energy density operator. And now we consider the subsystem of a thermodynamic system, which is in a thermal state, and it's characterized by the temperature. It possibly can also be characterized by some chemical potential. And we just consider a system of spin half particles with some masses. And now you can use a textbook material. You can define your field operator. You know what are the annihilation and creation operators for such simple simple model or whatever you call it. And now you can try to perform the thermal averaging. For that, you just need to know this product, the averages of these products of annihilation and creation operators. These are sufficient to calculate the thermal averages of needed for the fluctuations. And now you also define the operator that will represent the energy density. This will be just integral over the volume of the T00 component, and it's kind of modified by this kind of Gaussian-like profile to avoid the problems with the edge at the edges of the system. And now you can determine the fluctuation of the energy density of such subsystem. And now you can study what will happen if you change the size of the subsystem. And the characteristics for us was this the variance, which will be basically a function of the size, the mass of the particles. Yes? Yes. Well, this is yeah. So basically, this is uniform. This is uniform. So yeah, I know what is your where are you going, but you can define the variance. You can define also the standard normalized standard deviation, just to make the analysis simpler, and then using the time component of the canonical energy momentum tensor, you can find the thermal expectation of the operator, and then you will see that actually the thermal average of T00 for canonical, it's basically giving you the energy density of the system at this as a function of this variables which I gave here. But what is funny is that actually it agrees with the definition of the elementary kinetic theory, and also you will find that whatever the usual pseudogauge you plug in, you can calculate this quantity for the HW, GLW, and other pseudogauges. You will see that all of these densities are the same. Yes, yes, something which is you expect. Yes, yes. So this is something that you would expect to have, which we just as a kind of check of the sanity of what we are doing actually. And then you can proceed and try to calculate the fluctuations. And now surprise comes because the fluctuations calculated for all these different pseudogauges are different. So basically, this is what you get. You have a size of the system. We just took a size from 0.2 Fermis to 1 Fermi as a kind of, I don't know. We just took it as a kind of usual scale that one picks to define the coarse graining in the hydrodynamics, actually, because usually you go even below this. You go, I mean, below 0.4 for sure, but usually the coarse graining is on the level of 0.2 to 0.4 Fermi, and then you will see that actually if you see what is happening in this regime, these fluctuations are huge. Yes, at this scale. At this scale of the system in certain temperature and mass. Temperature and mass in equilibrium, in thermal equilibrium.
Because the 2-point function,
yeah,
the stress energy tensor, also with the viscosity.
Yeah.
Viscosity depends on
this is your paper with Leonardo.
That means that if you consider me,
yes, yes.
Then you get okay.
Yes.
Everything agrees.
Yes.
Second order,
so
without say rotation, just homogeneous. Sorry, second order. Second. 2-point functions.
Yeah, you can. Yeah, you can actually. We did this exercise even for correlators.
Yeah.
And we found that exactly the same. Actually, guys did it in a very sophisticated way, much more complicated that we asked them to do it, but they found exactly the same property. And what is nice is, of course, when you go to the large systems, this all goes to the usual kind of statistical definitions from the kinetic theory. And then you can also find that if the masses are large, so basically you have a system which is non-relativistic, then also this they start to agree. So something that you would expect, but the problem is the scale in here. Because first of all, they are all different for all different pseudo gauges. And secondly, I mean, if you go to small systems, all of them fluctuate like crazy. And now the question is the following. First, how do we solve this problem? Because you said that we can always define construct your observables in such a way that you would like to get rid of this problem with the pseudo gauge, but I don't see a way to get rid of out of this problem. And usually if you have hydrodynamic theory, you really want to define what are these currents at this scale. Those pictures that I showed in the first slides are not just my drawings. This is what we are using to run hydrodynamics. We need this initial state at this scale. So if the energy density fluctuates like this between different pseudo gauges, which one we should use? This, yeah.
One might say that, okay, with hydro is starting with mean value.
I agree. But?
Okay, yeah. So of course that if you go very short.
Okay, so okay, I can follow. I agree.
Very small scale, then you will have large fluctuations of pressure.
Yeah. This is a quantum fluctuation. So basically, okay, one could follow this idea and could use this as an input for fluctuating hydro to have a kind of idea of the scale of fluctuations that you would get. But still, you don't get rid of the problem that you have this fluctuations completely different for different pseudo gauges. I agree. But how do you decide which one you to pick? Well, okay, what is your language?
And then it should happen that when I change pseudo gauge, the original fluctuations get mapped to the correct fluctuations of the other theory, which is indeed what happens at the theory level, right?
Okay, so you want to, okay, so yeah, I know where you are going. On fluctuations. Okay, problem. Okay, so I just wanted to pick this up because this is completely unrelated to the spin, kind of. I mean, I just consider the energy density which we are used to deal with when using the usual, doing usual hydrodynamics. Okay, I'm sorry, I don't know where I'm at. When should I conclude? Kind of now. Okay, so only one thing I'm left with at the very end. You have this different pseudo gauges. You know the prescription. You just plug in superpotential, and you get new currents. So you may ask yourself a question as follows. You can decompose this superpotential with respect to the force velocity. This is identity. Basically, you decompose along and orthogonal to the force velocity, and you can get this decomposition. The first part is people used to call it the phenomenological part, and then there are these different parts. But basically, this is identity. Now you can. Oh my God. Now you can do the same with the T mu. This is something which we all do all the time. So we decompose it along and orthogonal to the force velocity. You have different components, and now you can do it before and after pseudo gauge. And this is the translation table for symmetric to symmetric transformation. So your energy density, pressure, heat flow, and shear stress tensor would be modified doing such pseudo gauge in this way. So you have many terms depending on what is the structure of the superpotential. And now we ask ourselves a question, because this is not really easy to conclude, I mean, to infer anything from this. So we restrict it to symmetric transformation. So symmetric T mu to symmetric T mu, and then this equation should be satisfied. So actually the superpotential phi should be conserved. So it should follow the same divergence equation as the spin tensor itself. Okay, and then actually you can ask yourself a question, how you can, I mean, because this is still complicated. So you may take the case of the usual hydrodynamics, and you can try to construct pseudo gauge out of the fields which you have at your disposal. So usually in the simplest case, you have the temperature, chemical potential, and flow vector. So you restrict to this case, and you also can restrict to this transformation in such a way that your transformation will give you energy momentum tensor with up to first order gradients and not more than that. So, and this restricts the transformation a lot. You will see that only this kind of form is allowed. So you have a single scalar which will parameterize the whole pseudo gauge, and then this condition has to be satisfied. So the divergence of this must be 0. And this is, of course, not possible to satisfy in general, because this is a single function, the single scalar function, and you have 6 equations. So it's not possible to have this transformation constructed in this way as I described. But in the one-dimensional Bjorken expansion, this is actually satisfied automatically, because the for acceleration is 0, this tensor is 0, and also these parts are 0. So this constraint is satisfied, so it's okay. And then you can ask yourself what will happen with the system if you introduce such scalar component of the pseudo gauge. I don't have much time, but maybe I will just skip to the very last point. If you do some simple mathematics, you can, for non-conformal system, you can derive this differential equation. And this equation allows you to determine what is your I function which parameterizes pseudo gauge in the Bjorken expanding background. And then you can plug in the equation of state from whatever your favorite theory is. We took just relativistic gas of massive particles, and then you plug in the viscosities for bulk and shear, and you can solve this equation numerically, and you can find that actually it is pretty much allowed. But what you can see is that in this very simple system, both bulk and shear viscosity are modified at the same time, but they have to be compensated with respect to each other. And this is something which you can easily understand, because if you come back to this equation, which was here, you can see that in the Bjorken expansion, you cannot actually distinguish between the bulk and shear viscosity, because the system is one-dimensional. So basically, we found that, yeah, you can perform pseudo gauge. There is some residual, as we call it, pseudo gauge, which allows you to modify the shear and bulk viscosities, but the two actually are always kind of conserved together. Okay, the summary. I would say that apart from trivialities, that pseudogauge is interesting and probably worth some study. Is that first of all, I would say that the most important conclusion from all of these points is that whatever your pseudogauge is chosen, it should satisfy the algebra for the rotations. It also allows to gauge the densities in the currents, and in particular the energy density, and you will see that the fluctuations actually are strongly depending on this. And this is in a kind of agreement what Francesco found some years ago with Leonardo for the dissipative coefficients. And there is some residual pseudogauge which is possible to in the Bjorken expansion, but it's very much very restrictive and kind of trivial in this case. And yeah, I mean, this is more or less what I wanted to maybe discuss today. Yeah, so this is, I mean, in this particular case, we just focused on the commutation relations. But I agree, this is not a, I mean, this is not a Lorentz covariant tensor. That's true. I mean, personally, I would say that I would somebody like to really concentrate who are doing the calculations, the numerical simulations, to concentrate on the fact that those fluctuations are so much pseudogauge dependent. Because if we don't solve this problem, I think going to this discussion of the spin construction and including even spin in this picture is even adding more steam. Yes.
Yeah, last week we had a discussion session of this, and at some point I mentioned that we have a similar pseudo-gauge ambiguity in the charge current.
Agree.
Right. So that you have.
But this is a different story, in my opinion, because this ambiguity is also at the level of you know, you define your Lagrangian in terms of this is what you mean in the electrodynamics, or oh, sorry. Oh yeah.
So for instance, you can redefine the electric current. Instead of psi bar gamma mu psi, you can define it with psi bar gamma mu psi plus some unknown coefficient.
Agree.
And then the divergence of the magnetization tensor psi bar sigma mu psi. This is perfectly, same relation of this pseudogauge transformation gives rise to the same charge. But the difference is that this is not the current which must appear in the QED equation. So there is a coupling between the electromagnetic field and the current, and only then works. And therefore, in this case, the pseudo-gauge ambiguity is removed by a coupling with a field, which is the electromagnetic field. And this is also easy to understand in terms of an ideal experiment. So if you say, the electromagnetic field is created by the coupling with this particular current. This can be probed by using, say, a small electric charge and measure the force acting on it.
I agree.
So in this respect, you may try to carry this over to this ambiguity in the definition of stress energy tensor and say that, okay, we have a theory which is Einstein's, where the source of the geometry is the symmetrized minute.
Yeah. Yes.
Therefore, in this respect, one has a preferred pseudogauge. So, with Benefante, as long as we believe in the general relativity, should be the preferred source.
Okay.
Then you have a counter argument, I guess.
Which I don't want really to give. I mean, first of all, it's classical theory, and there is now, so far, there is no way to falsify this, what you say. I mean,
in principle, you can make a measurement. In principle, I'm not saying practice, but in principle, you could make a measurement, so you can prove that Einstein, I'm sorry, you can prove, so you have there are alternative theories of gravity. That would be,
sure.
okay. And these alternative theories of gravity
Are not falsifiable yet, and maybe ever.
They are not in practice.
In practice, not.
They're not in practice. Principle,
Okay, so you're okay, but doesn't mean that we can because it means that you need to perform an experiment. But we are doing this experiment, right? And we basically we need to. I mean, this is much more complicated experiment, of course, than just putting your electromagnetic probe and probing the interaction. But okay, let's thank you.